Let's continue with our discussion of chapter 1, diodes. And let's see, Firefox. Where is my OneNote? Oh, there it is. Yeah, I believe we stopped here. So let's bring it up. OneNote. Okay, so we talked about P-type semiconductors, N-type semiconductors, and then what happens when we combine the two types of semiconductors together. We obtain a P-N junction diode, and a P-N junction diode, if we apply positive voltage to the P-type material, negative voltage to the N-type material, we call that as forward bias, meaning there is current flow that occurs, and current flows through the diode and the circuit, which was here. And then if we connect the negative end of a voltage source to P-type and positive to the N-type, then we say that it's reverse bias and there would be no current flow because the depletion region is expanding. So the exact opposite happens here. You have P-type holes here, and you have negatively charged electrons, and opposite charges attract. So the holes and electrons are pulled away because of the external applied electric field, and the depletion region expands. The only current flow that takes place is due to minority carriers. So I'll talk about that a little bit. It's very low value, very low in value. Typically, it's in nanoamps to the femtoamps range, very, very small. Okay, so what are minority and majority charge carriers? Well, in a P-type material, we introduce column 3 elements, right? Column 3 elements, and so there are excess positive charges. Excess positive charges, meaning extra number of holes. But we still have the intrinsic electrons that are present in a P-type material. We have holes as well as electrons that are able to move. So both of them can carry charges. Hence, they are called as charge carriers. Electrons, of course, carry negative charge. Holes carry positive charge. In a P-type material, as well as an N-type material, both of them are created out of intrinsic semiconductor, meaning due to thermal effects, we already have electrons and holes that are present in that semiconductor material. Then we introduced column 3 element and column 5 element to create P and N-type materials. So now we have an excess of holes and an excess of electrons in these semiconductors. But there's also the intrinsic charge carriers that are present because of thermal effects. And so in a P-type material, there are excess of positive or hole charges, positive charges. Those are the majority carriers. But there are still intrinsic electrons that are present. And so those are low in number compared to the externally introduced dopants. Hence, those are known as minority carriers. It's simply the majority and minority is simply the number, the absolute number of electrons or holes that are present in a material. So it's a P-type semiconductor, excess of holes, majority carrier are holes, minority carriers are electrons. In an N-type material, it's the exact opposite. We have an excess of electrons, hence electrons are the majority carriers, and holes are the minority carriers. Okay. So in p-type material, holes are majority carriers. Electrons are minority. And in an n-type material, electrons are majority. And holes are minority. So the current flow that takes place in a p-n junction diode can take place due to both the flow of electrons as well as the flow of holes. Polar opposite charges, positive and negative, but both of them are crossing over at the same time. Okay. And the same effect also occurs in transistors, specifically the bipolar junction transistor. And because the flow of the flow of current takes place due to two separate charge carriers, these are also known as bipolar devices. Okay. So diodes also is the same. In BJTs, that is chapter 2, we have bipolar junction transistor. It's in the name itself. It's the reason is because it takes place due to the conduction of holes as well as electrons. But this is true of the diodes also. Okay. So in reverse bias, the only current flow that occurs or that takes place is due to the presence of minority carriers in both the p-type as well as the n-type. And because the minority carriers are very low in number, the actual value of the current is also very, very low. Typically, it is in the nanoamps or picoamps or femtoamps range. Without a specialized setup, we are not able to even measure this current in the lab. Okay, it's so small. It is also known as the saturation current. Okay, saturation current. Yes. So question being asked is, where do the minority carriers come from? They are the intrinsic carriers present in the turtles. The dopants would be external. Dopants would be external. All right. Any other questions? Okay. So we can make a mechanical valve analogy. We can compare a mechanical flap valve and explain the operation of a diode. It's a one-way device. If the fluid is flowing in this direction, from left to right, the fluid flow pressure will cause the valve to open up and fluid is allowed to pass through. In the opposite direction, the fluid flow is coming in this direction, then it blocks the valve or blocks the passage because the valve is now forced shut. So a diode is analogous to a one-way mechanical valve. It only allows electric current to flow in one direction, and it blocks the flow of electric current in the opposite direction. So it's a one-way device. Okay, it's a one-way device. This is another way how this is another way where the diode is different than a resistor, capacitor, or inductor. A resistor, capacitor, or inductor does not have any polarity. You can charge the inductor or capacitor or allow current to flow through a resistor in either direction. They are not one-way devices. Okay, so that's a diode analogy. Now, if we plot the voltage for a diode versus its current, if we plot the current for a diode versus its voltage, meaning as a function of the voltage, we get what is known as the VI characteristic, where voltage is on the x-axis and current I is on the y-axis. In a resistor, in a linear device, you have something like this. So VI characteristic for a resistor or a capacitor or an inductor for that matter is linear. If you increase the voltage, the current increases. If you decrease the voltage, the current decreases, and vice versa. For a diode, not so. If I zoom into the plot in the forward bias, this is how it's going to look. This is V and this is I. If you increase the voltage for a long time, nothing happens. It's basically zero. Okay, it's basically zero. Remember, we talked about the depletion region, right? Depletion region is a barrier that is built in, meaning the moment we create the PN junction diode, holes and electrons diffuse, they recombine. There's a region that is deployed or depleted of all charges, and then it gives rise to an electric field. That electric field opposes any further diffusion of the charge carriers. And so it comes and stabilizes to a certain level. And depending on the material we use, that level is fixed. For silicon, it's about 0.6 to 0.7 volts. For germanium, is between 0.2 to 0.3 volts. And so as long as the voltage that is applied to a silicon diode is less than 0.6 volts, the current will always remain zero, or as close to zero as possible, which is right here. Approximately equal to zero. And then as it gets towards 0.6 or 0.7, it will start to rise. From that point on, even a small increase in voltage will give rise to a very large increase in current. In the intersection point right here, it's taken at 0.6 to 0.7 volts. So this is for silicon. Germanium is somewhere here. .3 volts. And this is germanium. This is 0 amps. Okay, this is the material property. Doesn't matter how big the diode is, how small the diode is, the physical dimensions do not matter. Okay. So primarily based on the material that we are using to create our diodes. And so this is the forward bias region. Positive voltage being applied to the diode, you obtain a positive current. Okay. So the voltage, the voltage that is required to turn on the diode, meaning to permit the flow of current is also known as the turn-in voltage, the turn-on voltage, the knee voltage, or simply the diode voltage. Okay, so there are several different names that can use for the exact same quantity. So this is known as the knee voltage, turn-on voltage, oftentimes simply referred to as the diode voltage. Technically, it would be the diode turn-on voltage. Okay, diode turn-in voltage or diode turn-on voltage. And we will simply refer to it as VD, diode voltage, VD. Okay. All right, any questions so far? Okay. In the reverse bias, if you apply a negative voltage to the diode, then we have no current flow. So this is exaggerated right here. Saturation current, but it is exaggerated. Exaggerated saturation current. It's typically nanoamps or less, and so you will not be able to measure it. Simply comes up as 0. Now, it will stay off in the reverse bias until if you keep applying large amounts of reverse bias voltage to a diode, at some point, the PN junction is going to break down, right? They are being pulled apart. At some point, it's going to break down, and a large number of charge carriers are going to flood through the junction. Typically, this voltage for a regular silicon diode is about 50 volts. There are diodes that can go up to like hundreds of volts. It goes from 50, 100, 150, so on and so forth, all the way up to 400 volts. And then, of course, we have high power diodes that can handle much higher voltages than that in the reverse bias. In the lab, you would not have to worry about anything like that. Our power supplies go up to either 25 or 30 volts. Even if you apply 30 volts to the diode, nothing's going to happen. It's going to function just fine. But what happens at breakdown is the junction breaks down, which is right here. And a large influx of carriers cross the junction. They acquire enough energy that they are now able to cross the junction, and a huge amount of current starts flowing to the diode in the reverse direction. And that is indicated right here. Okay, indicated right there. So depending on the amount of dopant carriers that are present in there, whether there are, if it's heavily doped or lightly doped, there are two mechanisms where breakdown occurs. So in the reverse bias, if you create a PN junction with heavy doping, meaning there are excess of carriers that are present in both the P and N-type material, then the breakdown that occurs is typically around less than 5.5 or 5.6 volts. Let's say less than 6 volts. So you apply 6 volts in reverse bias, or sorry, 2 or 3 volts in reverse bias, less than 6, nothing will happen. But as soon as it goes more than 6 volts, it acquires enough energy that the carriers will cross over. And so that breakdown that occurs in less than 6 volts is known as Zener breakdown. And there are diodes. So Zener breakdown occurs less than 6 volts. And there are diodes that are specifically designed to operate in the reverse bias. And the reason is it can handle large amounts of current flow while keeping the voltage across it nearly constant. As you can see from the characteristic, voltage can now be increased. You can input voltage large enough, greater than that breakdown voltage, but the diode itself will hold its voltage constant. And we'll talk more about that when we get to the section on Zener diodes. But this is the operating principle. Once a diode enters that breakdown region, it can carry large amounts of current, and this is the reason why. Because the junction has broken down. Okay, so Zener breakdown requires that the junction diode be created with very high levels of doping. Or very heavily doped. That's what we call it, heavy doping or very heavily doped. This typically occurs for less than 6 volts. And then another process takes place that is known as impact ionization. And these charge carriers acquired enough energy that they now are moving around at random inside the material. When they move, they're going to collide with the other atoms, and they're going to displace more charge carriers. When they collide, let's say one collides with an atom, breaks 2 more and creates 2 more charge carriers to move out. Those 2 in turn will create 4, will create 8, and so on and so forth. And so there's an avalanche of free charge carriers that are created because of this impact. Hence, it is known as the impact ionization process. And this avalanche of charge carriers that are created because of these collisions, this is known as an avalanche breakdown. Okay. And so we have avalanche breakdown that occurs in the reverse bias. And this is typically larger than 6 volts, low or standard impurity doping. But over the years, what has happened is these two terms have like kind of melted into each other. So anytime reverse breakdown occurs, it is just generically referred to as Zener breakdown. Whether it actually is Zener or not is irrelevant. So sometimes we have to be careful in what we are defining. Okay. So again, Zener breakdown occurs in heavily doped diodes. They are specifically designed in such a way that breakdown occurs. And then there's impact ionization that occurs larger than 6 volts, meaning you're increasing the external electric field. That energy is imparted to the free charge carriers. Now those in turn have enough energy to move. And once they're moving, they just move at random and they collide with other atoms and create more and more charge carriers. It leads into an avalanche effect, and then it leads into breakdown or junction breakdown. Okay. Let's see. Symbol of a diode we already talked about. These are the references for the diode voltage and the diode current. If we say diode voltage, that means the reference, the positive reference of the voltage is always at the anode, the negative is at the cathode. Okay, so if it's a Zener diode, VD is always going to be negative. Okay, Zener voltage would be positive, but the diode voltage for a Zener diode would be negative because the reference is always taken at the anode. Positive reference at anode, negative at the cathode. And current flow for a diode is also labeled always as flowing from anode to cathode. Okay, so right now we're going to work just with regular diodes, not with Zeners, but the reference always remains the same. Anode is always positive, cathode is always negative. So that doesn't change. So reference polarity and direction. Okay, I think we're almost out of time. Load line analysis. Okay, all right, let's just stop here for today and we'll pick up again on Wednesday.